Yeah, this is actually going to be a workshop. So the first half is going to be just a reminder of what we covered in the workshop. This is around optimizing using NumPy. All of you are probably using NumPy, but are you really using it effectively? And that's what we're going to be looking at, is replacing loops effectively. And so explicitly today, we're going to be talking about aggregations, universal functions, broadcasting, and a quick example on sorting using NumPy and stopping doing your own loops and use the things that have been optimized. And so this is the goal. Let me see if I've got my, um, okay, there we go. Now I can advance. Learning objectives. So this is the idea. You're going to learn how to do a loop replacement strategy. So it's search and destroy. You're going to look for those loops that are taxing, the ones that have big trip counts, doubly nested, triply nested loops, so forth. Even when they have conditional logic in it, you're going to see some examples of how we can handle that. And there are thousands of functions that have been written in C that take advantage of the SIMD underlying vectorization primitives, typically implemented through Intel's oneMKL that comes as a part of the stock package of NumPy. And so update your NumPy and get the most recent versions to get the best performance. But these are some of the things we're going to look at doing. How do you do broadcasting, aggregation, sorting, reductions? Um, uh, Not a SQL where and select, not those, different context altogether, but a NumPy where and a NumPy select. And we'll see how to get around conditional logic and still get our vectorization goodness. So this is some of the things that we're going to be covering today. It's going to be hands-on, but we've got to get some of this preliminary stuff out of the way so that you know how to do the lab, so you know what the magic sauce is and what to start looking for. So I just want to start with sort of an overview of the Intel AI Analytics Toolkit. The toolkit is comprised of various components that, for the most part, are upstreamed into the stock versions of the equivalent thing. So, for example, Intel optimization for TensorFlow, Intel optimization for PyTorch. Yes, the stock version of PyTorch has many of our optimizations built in through the oneDNN library, which is part of the Intel AI Analytics Toolkit. But it may have some other ancillary ones that may have oneAPI or different parts, but it takes advantage of those technologies. But the cadence at which, let's just pick on PyTorch for right now, the cadence at which the stock version of PyTorch is updated, it's a community-wide thing, right? So they don't update at the same cadence that we're creating these new instructions and doing the optimizations and doing those things. So the advantage of the toolkit itself is that you get the latest and greatest, fastest, kind of a thing that you're going to be using. Those things do find their way upstreamed into the stock versions of the tools. So for example, for PyTorch or XGBoost and so forth, those things get put in there. But I just wanted to kind of point out on the deep learning side, some of the things, we're not going to be covering that today, but TensorFlow, PyTorch, the Intel neural compressor to optimize for inference against Intel CPUs, GPUs, what have you. And then on the machine learning side, and some of you have come to the talks that I gave on, and Praveen and I did together on Intel extension for scikit-learn, which is an extension, an extra library that you download, 2 lines of code, and you get incredible performance gains, both for the fit and predict functions for a number of things. And then the, for the common suspects, the principal components, the clustering, dbScan, k-means, k-nearest neighbor, random forest, all those things are optimized. You add 2 lines of code and off you go. By the way, you can also target GPUs, Intel GPUs with that as well. So you can run those on other devices. We've already done that series. And so XGBoost is another thing that we've optimized now that we put all of our optimizations to the upstream version of XGBoost, and we've got some training on that if you guys are interested later. Data analytics, I won't be touching that much, but we have a distribution for Modin, which is kind of sorta a replacement for pandas. It can handle distributed computing, so you can have data frames that are larger than just what you can stuff on a single node, and so forth. I won't be covering that. What we are going to be covering is the thing in red. It's the NumPy library, and what's built on top of that also, which is the SciPy library. So we'll stay an example there. And then also pandas, which I'm going to show you how to take advantage of some of the tricks I'm showing you for NumPy to actually accelerate a pandas apply with conditional logic in it. And then Praveen has done any number of talks on NumPy and data parallel Python. This is the span, but we are looking specifically at this NumPy thing today. And so this is kind of the goal. I'm just going to keep driving in. We're going to be using the Intel Dev Cloud. And so what I would recommend, and Praveen probably also has that link, it's up here, it's devcloud.intel.com/oneAPI. So there's different flavors of the Dev Cloud. There's a RenderKit version and an OpenVINO version, and there's all kinds of different versions. You want to make sure that you're registered and logged into the oneAPI version of the Dev Cloud, get_started. So if you go to this URL right here, and Praveen can probably put that in the chat link for you, then you can go ahead and log in. Hopefully you're already enrolled in the Dev Cloud. And so all you do is you click this little icon, go to that page, scroll down to the bottom left, and you'll see this Jupyter icon. And it will either say sign up if you haven't signed up for the Dev Cloud yet, or sign in, I mean. So sign in. But once you do sign in, then that little icon there will change to something like launch Jupyter Lab. And so when you launch that Jupyter Lab, and I'll show you how to do that in a little bit, then we'll be good to go and you can start playing. So I would recommend that you do this right now as I'm preparing to go through the talk. Go ahead, log in, and begin letting Praveen know, thumbs up, yes, I got into the Dev Cloud, or hey, there's an issue or whatever. And so hopefully we'll all get in there easily. So the topic for today is NumPy, powered by oneAPI. So all that oneAPI goodness we've been learning about, gets baked into, it's all based on those compiler technologies, SQL, all that stuff at that C level, can take algorithms and compute with them and optimize for cache utilization, for SIM devectorization, for all these kinds of things that can be adaptable even across different platforms. So it can run as good as possible on XYZ platform, ABC platform, whatever it is, through the sort of the auto vectorization capabilities that come with the compilers and so forth. So what we're doing is we're taking advantage of one of the libraries built in such a way with a lot of expertise, and it's the oneMKL library that under the hood gets rolled into in the stock version of NumPy. That's the thing that you leverage, and so or take advantage of. So NumPy, that stock version, has the API, the Intel oneAPI, sort of goodness baked into it. But like I told you, if you wanted to just download the analytics toolkit, you could do that. It's already on the Dev Cloud. So are you getting the performance you expect using NumPy? Because most of us, I was programming in Python, and from my earliest codes, I'm dealing with numbers. I'm a data scientist. And so, you're using NumPy. It's there. Yeah, yes, import NumPy as a NP. Okay, it's there. So I'm good, right? Well, let's talk about that. And that's what this talk is all about. Are you using it effectively? And are you keeping your NumPy library up to date? So these are the questions that we're going to be addressing. Now, at the start, I just want to tell you that I used to be a Fortran programmer, and then I turned into a C programmer, and C was my lingua franca. I mean, that's what I loved to program in for the longest time. Migrated over to C++ some years ago, and boy, there's a lot of cool things about that. But I migrated to Python maybe 10 years ago because of doing data science, and a lot of the examples are built for Python. So what I fell in love with Python for is because it's easy. It's so great for rapid prototyping. One of the advantages of Python is that you don't have to worry about your data types. So you can just start coding and slinging code around. It's great for a hacker, right? And it's fast because of that. Fast insofar as getting your ideas into code, okay? You can tackle just about every imaginable coding task. It's get a project rolling very quickly, see an example somewhere and grab it and stuff it in. You can really get moving rapidly. It's dynamically typed. This is the thing I'm talking about, which makes the programming easy. You can leverage a huge number of libraries for science, for math, for engineering tasks, and we're going to be talking about some of those today, just a few. And for AI, it's fast. There's no porting. Like, um, you target in Python. I worked for another company that was on a completely different architecture than the x86. And my Python code that I would run for my AI projects ran there, and it also runs on x86. It's highly portable because it's built on abstractions that get implemented on these other architectures. And so that is all cool, and I love it. I really like Python, but Python is also very slow, and it's slow at certain things, okay? It's not universally slow, but it is slow at a lot of the important things we in HPC care about, okay? That is repeated low-level tasks, large loops, nested loops, even list comprehensions if they're large. And this, we're going to go into some of the reasons for that, but there are ways to mitigate that slowness and that weakness, okay? And it's very slow. It's not just a little slow, it's very slow, and I'll talk about some of the reasons why. So if we use a numeric library and take full advantage of it, we mitigate the slowness and we get all that goodness that I talked about from before. And the solution here, I'm arguing, is NumPy, powered by oneAPI. And let me go into some of the reasons why. And one of the key reasons is based on this idea of vectorization, okay? Now, many of you come from C++ land and you have a certain idea in your mind about vectorization. And yes, I am talking about that. In Python, however, it's a little bit broader than that. They may call something vectorized, even though technically at a C++ level, it has anti-dependency or flow dependency or whatever that prevents you from literally vectorizing. But you get these, quote, vectorization benefits anyway from using the C compiler with the high-level memory optimizers and all that kind of stuff, and just getting, oops, I clicked the wrong button. I leaned my arm on the desk here. So you get some of these benefits from Python, and in quotes, what's called, vectorization also includes sort of like these C++ memory optimizations, cache locality, memory being contiguous, okay? So that's part of the loose definition of vectorization in Python. It includes both ideas. So this practice, now this is a quote from Wes McKinney. Well, he is the big brain and maintainer and the guy that sort of invented pandas, okay? So he knows a little bit about this stuff, and he says that this practice of replacing explicit loops, which is what we're talking about today, with array expressions is commonly referred to as vectorization. In general, vectorized array operations will often be one or two or more orders of magnitude faster than their pure Python equivalents, with the biggest impact seen in any kind of numerical computation. And you're going to experience that today. So vectorization is not just a theory, okay? You're going to see and play with some of these things, and you're going to see maybe a modest 4x here or there, but maybe a 10x here or there. But a lot of the examples we're going to be going through today, you're going to be 1 to 2 orders of magnitude, sometimes faster than that. Okay, so because it's a loop replacement strategy, and we're gonna kind of show you what that means in code. Okay, so now why are these speed ups so dramatic? So one of the reasons is because NumPy, using oneMKL under the hood, which is powered by oneAPI, and that what comes with that is all that cache locality, contiguous memory availability. You take advantage of because you see Python just by and of itself, and when you create a Python list, let's say of 100 elements, and you put integers in there, 1 through 100. Okay, great. You've come from C land, and so you just automatically think that all that is in contiguous memory somewhere. Well, it's not in Python, okay? Or it doesn't have to be, and as a general rule, it's not. And every one of those elements, when you access it, is basically an object. It has a reference counter, and so you have to figure out what the data type is, because just because you put integers in that list, the rules of Python say, well, yeah, but you could replace element number 2 with an image instead of an integer. And you could put a float over here in element 17, and you could put some big blob of whatever in element 99. And so every time you touch that list, it has to go look up Well, what kind of data types am I in? Where's my reference counter? It's doing a lot of stuff. When you're only dealing with a small list, no big deal. It's a small tax to pay. But when you're dealing with 1,000,000 elements or 1,000,000,000 elements, those taxes add up, and it adds up in a hurry. Okay, so this is one of the reasons. Okay, so what I'm articulating here is why the one MKL is so much greater, and that's because for one thing, when you're using MKL under the hood, when you bring that list in, you convert it to a NumPy array. It's going to put it in a contiguous memory. It's in C. Okay, so it's going to be contiguous memory. You have a huge advantage right there because now you have access to cache locality, temporal references, all that kind of stuff that the HLO, the high-level optimizer, and the compiler can take advantage of and give you the best access patterns. So this is one of the reasons. The other reason is because I'm not talking about threading right here. I'm talking about the vector lanes. I'm talking about how many functional units are on even just one core in a CPU. Just one core. If you're talking about AVX2 machine back in the day, you had 256 bits. So that's like 8 floats wide if I did my math right. So you could operate on a single core, one thread, you could operate on 8 floats simultaneously because of the wide vector lanes. Well, then coolness happened in that we created wider vector lanes for the AVX 512 land. Okay, so now all of a sudden you've got a 16-lane highway. Now this is per core, per thread, all right? So you've got one 16-lane highway. You can do a lot of stuff. And if you are clever in C and you transform your loop to be, instead of accessing that loop element by element one at a time, it grabs 16 elements at a time, which the underlying architecture allows for. And in fact, our cache lines are built around this principle. You grab them at one chunk, and you can do all those operations in, say, one clock cycle for 16 of them. So you're not limited by that sequential nature. And this is per thread. I want to emphasize that it's different from threading. So this is SIMD in a nutshell. Let's say we want to add the two arrays A and B together to get an array C, a vector. Well, in traditional Python, the loopy approach, what we would have to do is go to element A, read it. Oh, it's an integer. Okay, what can I do with integers? Okay, I think I'm ready to get my reference counters. Okay, now read element B. Okay, what is it? Oh, it's an integer. Okay, what can I do with it? Okay, yes. Okay, now add those two things. Okay, great. I'm going to put it in element C. Well, what kind is that? Okay, well, let's update the reference counter. And then you go back and repeat, rinse and repeat, rinse and repeat. And that's slow. For this small list, it's no big deal. For 100 elements, maybe it's no big deal. For 1,000,000 elements or 1,000,000,000 elements, this is a huge deal. Okay. So we want to take advantage of SIMD. What SIMD does is it says, hey, I have, because this is now in oneMKL, it's in C, these memory elements now, since you put them in a NumPy array, are contiguous in memory. Okay. And now we can take advantage of the fact that the hardware loves to pull in a cache line at a time from that memory. And so it's going to pull in, let's say, 16 elements at a time. I'm just showing maybe 8 here. But it'll pull in all 8 of those simultaneously in one SIMD instruction. It'll pull the other 8 elements in one instruction, SIMD, and then it adds them and stores them. And this can all be done sometimes in just a clock cycle or maybe a couple. Right, so you're getting lots of parallelism built in through SIMD, and this is not vector. This is not threading. This is not threading. This is not because we're taking advantage of multiple cores. This is what each core can do. Okay, so it's an important concept to remember. And so, so this is some of the stuff I was talking about. That cool thing that we liked about being able to program so fast in Python because it's dynamically typed. That's an advantage there for the programmer. It's a curse with respect to performance, right? Because you have to check the data type every time before you go to use it. And you have to update these reference counters and all this kind of stuff. And so and you have to do this for every loop iteration. You have to go through, boom, you pay a tax for doing that read of the first one here on the left. Then you have to pay the tax again when you read the second one. Then you have to pay it again when you just keep getting these taxes added up over and over and over. And it's very slow for large loops, okay? And then the other thing is what I alluded to is that in Python, when you have that nice little list with integers 1 through 8 in it, it's not guaranteed to be consecutive. They could be spread all over the place because they're just objects. So they have no relationship to one another. So now this is going to become important because remember I told you the underlying hardware, what it does when you're reading in an element, whatever this element is in memory, it's going to read in for free. It just built that way to read in those 8 or 16 or 32 elements that are nearby automatically. And we're going to get to that. So you're only going to use this little one right here. You read in 16 consecutive elements and you wasted them. And you went over here to 2. That 2 is not in that same memory reference anywhere close. So you read in the value 2 over here and you read in 16 elements to just get that 1 and you throw all the others away. And it's just a very silly way to approach life. It's very much like the following scenario. Let's say that you have guests over for breakfast, they spend the night and your guests are upstairs. They come down in the morning, sort of one at a time, and you ask them what they'd like for breakfast. Oh, they want an egg. Okay, great. So you go to your refrigerator. Hopefully it's in your refrigerator. Maybe you have to go down the street to a CVS or a Walgreens or a Walmart or something and buy the eggs. That would be like going to main memory or maybe going to disk, right? But maybe if you're lucky, the refrigerator sort of represents maybe some kind of a cache. I mean, I'm going to stretch to some analogies here, but you go to the refrigerator and you grab a carton of eggs. It has 16 eggs in it. And so you cook one for your guest. And so that's great. And all the next guest comes down and says, well, I'd like an egg, but I like fresh eggs. I don't want the carton that was already there. Just give me a different carton. Okay, so you go back to the fridge and you get another carton and you cook that egg. And then another guest comes down. Pretty soon your counter is filled up with egg cartons all over the place. And you've used one egg from each carton. Well, eventually your countertop can't hold all those egg cartons and you knock them on the floor. And those are called cache line evictions. Okay. And well, it's a disaster. Okay. And yes, you fried some eggs, but you spent a lot of time walking to the fridge. You spent a lot of time. It was just very inefficient. Okay. And so what happens is this is kind of like your cache line eviction. You knocked all those eggs on the floor and now you got a mess. Okay. And it's very slow, because you were given, it was served up to you on a table to have a full carton of eggs. Okay. And you only used one. Imagine instead the alternative. Imagine that when your guests begin coming down, you take a carton of eggs out of the fridge and you start cooking all 16 eggs at once. And then as they sit down at the table, you serve the eggs and you're done. And now you throw the empty egg carton away. Much more efficient. And you do this over 1 billion egg cartons, it starts to add up. Okay. So this is the other reason for this issue. And this is kind of separate from the SIMD aspect. This is really more dealing with memory and cache locality, the way your memory is set up. Are you setting up to read at the C level as a row major or column major? Are you accessing those memory elements consecutively, let's say in a matrix multiply? Well, a C programmer would never worry about that in modern day. They would just call MKL, which takes advantage of BLAS, BLAS level 3, and it would just do that matrix multiplication in the most efficient way, and it already knows about this stuff. Well, that's what we're doing because the MKL, the oneMKL, underpins NumPy. So we need to find that function in NumPy that lets us avoid all this cache line business, okay, all this bad usage of it, right? And then other issue here is that I alluded to it already, but an array of integers in NumPy, those are contiguous in memory, okay? And they're not in Python. So just by moving that data into the NumPy array, you're going to get some goodness. But if you continue to access that contiguous memory NumPy array from a Python loop and those loop iterations, it's going to still be incredibly, incredibly slow. Because Python, still is going to say, well, I need to do a num check, I need to do a reference. It's thinking. That's kind of the thinking behind it. So how do you improve your code patterns? You want to take advantage of all this good SIMD stuff. You want to take advantage of all this cache locality and memory hierarchy stuff and the high-level optimizations that come from the compilers that know whether you need to do loop interchanges and loop unrolling and do all that kind of stuff under the hood that you never have to worry about in Python. But somebody has to worry about it when you care about performance, okay? And so these library writers have done that. And so these are some of the things that we're going to address today. NumPy vectorization, which encompasses NumPy universal functions, ufuncs, aggregations, fancy indexing and broadcasting. We'll talk about that a little bit. The NumPy where and select. Now, this is not your old friend SQL where and SQL select. These are to handle conditional logic. And I'm probably not going to touch on are all loops vectorizable. I've kind of pulled that out. I may take this out of the slides before I give them to you, but we've got enough fish to fry as it is. So how do you create NumPy arrays? So many of you are familiar with this. You can just take your existing list from Python and stuff it into the NumPy array, and it'll create a ND array for you. ND in NumPy land stands for n-dimensional array, okay? Kind of like a tensor, not a physics tensor, but a programming tensor. But the dimensions are empty when you do that. So no, I'm sorry, but you can create an empty array by doing ND array and specify a shape, but you're not telling it. You can specify the type, float, int, whatever you want, int 16, 32, whatever you want to do. Or you can fill it with stuff. You can put in zeros or ones just automatically and get these things. So this is just how you create them, and I'm sure most of you are familiar with those and probably use those. Some of you may use ufuncs, but many of you may not. And I gave this talk back in December, I think it was, and a fellow was from Airbus Canada was in the audience, and he was intrigued after he went through this lab because he saw these speed ups that I was showing him, 10x here, 100x there, cool. Well, he had a project. He's a data scientist, and so he had some stress analysis data that he had for Airbus, and he was analyzing. It was taking him forever, and his colleagues were saying, "Well, it's Python. What do you expect? I mean, you're going to have to just rewrite it in C++." Well, he's not a C++ programmer. He was not that thrilled about that prospect of transforming that much code. So he thought, well, I'm going to just refactor it in the ways that we've done in this lab. And so he went on a search and destroy mission for those loopy parts of his code, and he replaced them with the equivalent NumPy arrays. His overall stress analysis code improved a factor of 60x. 60x. He was thrilled. If you could watch a guy doing a backflip, he reached out to me on LinkedIn, and he was effusive in how great that was. Okay, so that was not just a single kernel. That was his whole stress analysis code that he was dealing with. So look into it. There may be some surprises in here. Maybe you're not using it fully effectively, right? And so the kinds of things that you might want to look at are math operations, like the typical thing. You're going to add vectors, subtract vectors, multiply, divide, reciprocal, map, mul, log, exponent, square, all those transcendental functions you learned in calculus, all the inverse functions, the hyperbolic cosines, hyperbolic sines, all the usual suspects are there, okay? The bit twiddling things that you may do, bitwise ands and ors and XORs and inverting and shifting left and right and doing all that bit twiddling stuff can be done in a vectorized way. And so if you're doing that in a Python loop and you're slowly manipulating these things, you're shooting yourself in the foot. Comparison functions, greater than, equal, greater than, less than, blah, blah, logical, XORs, all those kinds of logic operations can be done on entire vectors. The bit twiddling can be done on entire vectors. The floating point functions, like you want to test whether anything in your vector of 1 million or 1 billion elements has an infinite in it, or a nan, and not a thing, or not a number, or is it infinite? You want to take the absolute value of everything in one fell swoop, or figure out what the sign bit is, or whatever. All these things, floor functions, all these kinds of things can be done on all billion of those elements. And under the hood, we're going ka-chunk, ka-chunk, ka-chunk with the SIMD, and we're using that contiguous memory, and we're getting orders of magnitude more performance by doing it that way. So the goal then, what you have to do is to figure out when you have a chunk of code, how you're going to, sort of replace it with a vectorized function. And so the idea here is that the oneMKL library that we use under the hood, underneath NumPy, every time we come up with a new vector instruction, like not too long ago, they improved the AVX instruction set to handle sorting better. And so NumPy, the sorting routine, got an automatic boost in speed. And so if you're doing sorting, don't do it the old, Python sort method. You use the NumPy sort, and you're probably going to see a significant speed up. So, those advancements that we make on those underlying architectures and creating new instructions in the instruction set, those find their way into oneMKL and oneDNN and all these things. And they're expressed to you in terms of packages such as NumPy, pandas, SciPy, and so forth. So keep those things up to date. But this is the kind of thing that we do. You want to truncate integers. Well, use NumPy to do that. Don't be doing, roll your own business, right? Sophisticated indexing. Now, this is kind of the fancy indexing thing. This is a way, and it takes a while if you're untrained to think in terms of what's going on here. But that : 2 thing there on the right, if I do what I want to do is fill the array B with every other element from array A. Okay, and there's times that you do this. For example, in AI, particularly, a lot of things in AI come from time series data. And time series, there's a lot of manipulation you have to do on timestamps because humans live their lives differently depending on different times of the day, different times of the year, different times of the week, and so forth. So you'll see it in stock things, for example. For example, stock markets close on the weekends. Okay, they're closed on certain holidays. So there's exception handling that you need to do a lot of times on data based on periodicities in the data. So stride of 7 to do certain things on Mondays or Fridays, or find all the weekends or whatever. So instead of doing, and so many of you may be dealing with that kind of stuff. And I would argue, because we've all done this, because it's stream of consciousness. You're programming stream of consciousness. So you bake this in, and I've done it myself. You bake your code in because you had, 100 elements, and you tested this thing out and it worked great. Okay, fine. Now you move to production, and all of a sudden you have 100,000, 100 million, 100 billion elements that you're dealing with, and all of a sudden you baked in a bad performance issue because you did the roll your own. Also, let me just point this out. I think I made a mistake in the code on the left. Can you guys see it? No, I didn't really make a mistake in the code, but the point is that what is on the left there is not very readable, not very maintainable. It is kind of, right? But not really. Not compared to the thing on the right. The thing on the right is very readable, is very maintainable. You do have to understand what it means. I'll give you that. You have to understand the syntax. But the result is more maintainable, because every time you have another line of code, you have a potential for security threat, for bad performance, mistake, whatever it be, right? And so by reducing the number of lines of code, you're shrinking that footprint and that exposure. And so in this case, by doing this, not only are you making more readable, you're making it faster, and you're making it faster on the current hardware. Let's say that you're running on your server at home, you're somewhere is AVX2 machine, so maybe you get a certain speed up. Well, then when you make this change, B is equal to A : 2 in that code, and you do this kind of transform, well, then when you move it to an AVX 512, or maybe you're on AVX 512, but now you got Sapphire Rapids, whatever, there's new instructions that are put into the underlying hardware. You get those benefits for free. So you're future-proofing yourself. It's faster now, it's more readable now, it's more maintainable now. And when the new architectures come out, if there's a benefit to be had from the new instruction, you get it automatically without having to do anything. So this is the reason for doing this stuff, right? Here's just a partial laundry list. Now, there's thousands of these things, and I don't know them all. You kind of have to do a Google search and see. You look at what your code is doing in your loop, and you ask yourself, what if I were to describe what I'm doing in that loop, what am I doing? Now go Google it and figure out if there's not a NumPy replacement. More than likely, if it's low-level manipulations like that, there will be, okay? So things like computing the mean, the standard deviation, the variance, the sum, the product, a cumulative sum, a cumulative product, mins, max, argmin, argmax, all these things have NumPy equivalents that will work on billions of elements and speed you up, orders of magnitude, typically. Okay, so NumPy aggregations, let's just talk about this. So if I were to just do a NumPy sum on an array A, let's say I've got a two-dimensional array A, it will return back a scalar, a single value that represents the sum of all the elements. Well, that's not very flexible. I want to have the sum of every row, or I want to have the sum of every column. Well, the nice thing is about most of these NumPy operations is you can specify an axis over which to operate. So you can see, okay, just give me this, I forget which one, and without looking at my code, I'll go show you an example, axis 0 or axis 1, or whatever it is, whether it's columns or rows, you can get the sums for each of those kinds of things. And so that is much more readable. Let's say that the goal here is to just compute the mean. Well, you have an array A, you just say a.mean, and off you go. You're done. On the other hand, if you roll your own code, and I'm going to argue that some of you guys, because I did, and I thought I was doing pretty good with the data science stuff, but this wasn't my goal. I wasn't thinking in terms of this. I had some small little thing, and so I computed my own mean like this, right? Well, it's very inefficient, and it's less maintainable. And so if you replace it, you get this benefit. Now, what we're going to show you here is the difference between the axis equals 0 versus axis equals 1. So in other words, you've got more flexibility. You have parameters within that NumPy manipulation that allow you to have different flavors of a sum, okay? So one flavor of the sum is along axis equals 0, in which case we're going to add up and get the sums for all the columns. When we say axis equals 1, we get the sum for all the rows, okay? And so there's a goodness just in that, right? And then here's just an aggregation example of taking the code on the left and just saying, well, you can replace it with a single line of code. So more readable. That was, and by the way, that you'll see this in our lab. That was 100x speed up from doing that, right? It's more readable, more maintainable. Cumulative sum. This was a 13x speed up. So on 100 million elements. So more readable, more maintainable, faster now, will be faster in the future if we come up with some faster, cooler way to do it. This is sorting. This is the quick sort example. And so your lab, you're going to play with quick sort, merge sort, and heap sort and see if there's any method to this madness. Like, is it really quicker? And how much more readable and maintainable it is. So here's one of the examples just from quick sort. Roll your own quick sort like this, not very maintainable. On the other hand, you put that tax on the library writers to do a good, efficient, and secure and effective sorting routine. And now you've replaced that with one line of code and you say, hey, by the way, make the kind quick sort. 87x speed up, more readable, more maintainable, right? And on and on and on. Now we're going to talk about broadcasting. Broadcasting is this thing where in traditional linear algebra, you can't just take a, let's say you have a two-dimensional array that has, 4 by 3, 4 rows, 3 columns, and you want to add a vector to that. That's 1 row and 3 columns. Well, in linear algebra, you can't really do that, but we do that in code all the time because what we mean is I want you to take that vector and add it to each row of that array. And this is called broadcasting. In this case, we're going down 1 dimension. I've got 1, 2, 3 vector, and I want to multiply a scalar. Well, effectively, in your mind, it's not saying that the underlying code actually does this. There's SIMD instructions that can handle all this kind of stuff for you. But conceptually, what it does is it's as if it is copying those memory elements, putting 2's everywhere, and now element by element, multiplying 2 by 1, 2 by 2, and 2 by 3 to get the final result. That's a stretch operation. That's in 1 dimension. So this is we kind of talked about it. I'll move on for sake of time. So broadcasting from in the 2-dimensional sense, and this just keeps adding up with more and more dimensions of the tensors that you build. But let's take a 2-dimensional one that's 4 by 3. and you want to add this 1 by 3 element to it. Well, then conceptually what we do is we stretch it. You think of it as copying conceptually, so you understand what broadcasting is. In your mind, you're going to have repeat copies, and it's not going to consume the memory space and that kind of thing, because there's underlying SIMD things that will do this for you. But conceptually, you have this duplication of the 1, 2, 3 of all those vectors, and now their dimensions are the same. 4 by 3 and 4 by 3, you can add those two and you get the result. And so this is the idea of broadcasting. Now, what it allows us to do, though, is to do things like doing outer products, which you will occasionally, I'd say maybe 5% of the time, maybe 1% of the time, but you will find reasons that you want to do an outer product of 2 arrays. Correlation is sort of an example of that. When you're computing a correlation, you wind up with a square matrix that's, effectively the matrix transpose times itself, and so you get this outer product. Well, if you were to roll your own doing that, it's very inefficient, not maintainable, and so forth. And then when you use the, oops, I jumped ahead. When you use that reshaping idea, so effectively this is like a transpose. We're taking A transpose. Now A transpose times A, if you just literally use the transpose, you may get just a scalar, a single value. If you do the reshape and you do this where it's n by 1 times 1 by n, you're going to get an n by n matrix. Okay, and so anyway, this is one way, and I left an example if you guys want to play with it for doing a pairwise distance calculation for Euclidean distances or Manhattan distances. You can take advantage of this kind of trick to compute those things fairly quickly. So now we're going to go on to the conditional logic discussion, and this is the NumPy where clause. Now this is not a SQL where clause. This is just saying, look through use NP where, okay, and you're going to look through your array, and you're going to look for a condition, a less than 5 in this example. And if a less than 5 is true, return the value a from those sets where that's true. Wherever a is greater than or equal to 5, instead return 10 times a. Okay, and this is the result of the computation. Just conceptually, this is what the where clause is doing. So it's kind of simple. The select clause is its big brother. Okay, the select clause handles more complicated logic, and typically you have a statement, a condition statement, and then a choice statement or an action statement, and then a default. And we're going to see this in the California housing data set in the lab, where and actually I'm using the where clause here anyway for right now for the California housing one. But here I put in a condition. Now in this idea, this is just a fictitious thing. I don't know what I was thinking, but at the time I thought, well, I've got the California housing data set. Let's just dream up a scenario. Let's say that in California, they decide to give a rebate. They want to stimulate the economy during the pandemic. And so what they're going to do is offer a rebate on houses between $250,000 and $350,000. I don't know where in California you can find such a house, but let's say that they did that, right? And so this is what the graph on the right would look like. If you were eligible for that rebate, this is what you would do. Well, how would you implement that in code? Well, in code, you would do it like this on the left for the brute force method, right? Or you could use the where clause and just say, if t is less than, the $350,000 and the price is greater than the $250,000, take $50,000 off the price, and to plot it, I didn't want large values on the axis just for prettiness, so I normalized everything by $100,000, but this just gives you a sense of how the where clause, and by the way, this was 20 times faster. And I think you'd say that this is probably more maintainable. We've got 1, 2, 3, 4, 5 lines of code versus 1. So, here's just another example where in DB scan, for example, DB scan is used in data analysis for AI projects quite a bit. It's a very powerful clustering algorithm. The nice thing about dbScan is that when it finds a cluster, it'll say, oh, that belongs to cluster 0. Okay, great. Oh, I found this other cluster based on the EPS values and the minimum number of elements that you've specified that should belong in order for a cluster to exist. You give it those two parameters, and it then will say, well, that belongs to cluster 0. These other dots over here, they're all grouped together. They belong to cluster number 1, number 2, number 3. But it reserves cluster -1 to be an outlier class. In other words, it's just some dot somewhere in a scatter diagram that doesn't really cluster. It's not a grape that's close to any other bunch. And so maybe there's 2 or 3 of them, right? And so typically you need to handle those differently than something else. And so you can use this where clause, for example, to process things differently. So you could say, well, wherever dbScan is less than 0, do outlier processing, otherwise process normally, right? So these are the kind of things that you can do. And so this is more complex logic when you're dealing with we're starting to build up a multiplication table. I'm using the broadcasting to create a multiplication table. I just take a vector 1 through 10, and I do effectively the transpose. I do that reshape so that now it's a vertical vector like this, 1 through 10. And if it's 10 rows, 1 column, times 1 row, 10 columns, I will get a 10 by 10 matrix by using broadcasting. Well, then let's say that for whatever reason, we want to blank out all the products except for those that are a multiple of 12 or 9. Okay, so how would we do that? We could do that with a where clause. So we could, just say, well, if the multiplication table modulo 12 is 0, so in other words, it's divisible by 12, or if it's divisible by 9, go ahead and give me the product, give me the actual value, whatever it is, 24, 48, 72, whatever it is, but otherwise blank it out, make it 0. And so this is how you would do that. Now this roll your own versus, this is a 20x speed up, but it's the idea that the where clause allows you to handle conditional logic that would otherwise prevent you from doing the vectorization step. Okay. And so now select clause is the big brother. Select clause, our logic is starting to get kind of complicated. We got, ands and so forth. It's getting a little ugly. It's not as maintainable. So what we do in a select clause is that we create 3 different lists. It's a list of tuples. Really, I should probably by rights put parentheses around this, each of these things here, because it likes it that way better. And some things won't work without them. So I would put the parentheses in, but you have a condition list. This is your logic. Okay, so if x is less than 3, or if x is greater than 3, then do something. Well, the choice list is what you're going to do. You're going to be returning an array, but in this condition, x less than 3, you will return the value x. If x is greater than 3, you will return x squared. And then you can also provide a default choice, 42, the answer to life and everything, right? So what you do is every select statement is going to have something like this. You're going to have NumPy select, you can have the condition list, a choice list, and default. And then when you run, and this makes things incredibly fast, even for complicated logic. You're going to see in the lab here shortly, take some logic like this, even for pandas, you can apply this. And so take some conditional logic like this that's slowing down your apply statement like crazy. Well, we can do a condition, a choice, and a default, and issue that select statement. And I can assign that back to either my NumPy array or back even to my pandas data frame. And the result is about 20 times faster. In this particular little example, you're going to be surprised at how much benefit we get even using this in pandas in one of the labs on pandas. And I want you to play with it. So pandas, yes, it's built on top of NumPy. All the things we've described, you can basically take advantage of, when you're even using it. Pandas apply statements can be slow when you have conditional logic. When you have conditional logic and a slow function that you're applying per row, it can be really slow. And so you can use the NumPy select even around that, which is kind of a surprise. And so, I think you have fun playing with it. The methods, let's see. The other thing, you're going to get some benefit even using the NumPy select clause when you do not convert the data to a NumPy array, we see some benefit. But when you convert those numerical values in the pandas data frame using the toNumPy function, and then you do the select, things get even faster, quite a bit faster. And so, it's kind of interesting that how that works. But this is what's the idea of this one. This is just, here we're going to be applying a function right here called func. Func is this thing that has a conditional logic. It calls my function. My function is calling a log, which is a somewhat slower calculation at the low level. So, this is what we're trying to do. We're going to replace that with the following condition statement, choice statement, and default. Now, in this case, I just put the default right here. I encoded it directly as tuples. But condition, choice, and that default. And we call the select statement. And when I do that, this is a 200x speed up, more than 200x speed up from doing this. And this is with respect to that apply statement. So just before we get into the lab now, just a poll of the audience here. Maybe just by way of the chat, if you could just let Praveen and I know, are you using these kinds of things? Are you using parts of the AI analytics toolkit in your work, or do you plan to? Okay, are you using the AI analytics toolkit or parts of it in your current work, or do you plan to? And so the things I'm talking about are like NumPy and using these aggregation functions, ufuncs, these things that I'm talking about now. The Intel extension for scikit-learn, where you're going to be using dbscan or the optimized versions, dbscan or k-means or k-NNs, k-nearest neighbors, or random forests, or any number of those AUC, receiver operator operating characteristics, area under the curve scores, the train test splits, the principal component analysis, any number of those things from scikit-learn. Are you planning on using optimized versions of those? Are you planning on using Intel extension for TensorFlow, Intel extension for PyTorch to get that extra speed up, or are you just even using these same tricks I'm showing you right now with respect to NumPy? You can actually, many of those are also built into PyTorch directly. And so I'm working on a lab right now to show you the translation map between NumPy and PyTorch. You'll get, and in some cases, even more speed up than I'm talking about right now from using PyTorch, because we've built in those things. So are you using PyTorch? Are you using the Intel extension for PyTorch? Are you using Numba? The SciPy, are you going to be using, because you can get the optimizations for SciPy. I'll be showing you that later in another lab later, I think in June or July. So just by way of hands, or just by way of chat, if you could just describe, or just say, yes, we're using, we plan to use the optimizations for scikit, or we plan to use, like, this NumPy stuff looks intriguing, we may be using that, we may be using the PyTorch or the extensions for PyTorch to get some extra juice, maybe the Intel neural compressor, which takes models and makes them run much faster for inference. So if you just take a few moments to just raise your hand, say yes, we have that in our plans, or we're actually already doing that, that would be very helpful. And then now we're going to start diving into the lab. But as I dive into the lab, go ahead and let Praveen know, and then off we go. Let me shift gears here. Yes.
Let's give a couple of minutes break here and see if there are any questions.
Okay.
I don't see any questions in the chat section, but we'll just we'll just see if there are any questions that we can answer.
Great.
Just want to make sure I didn't miss any question in the chat. I'm not seeing anything in the chat, but just double checking on that. Meanwhile, you can open up your DevCloud and get ready with it.
So Praveen, can you see my screen?
Yes, I'm able to see your screen.
Okay, great. I'm going to start walking you guys through, how to get onto the dev cloud for one thing. So let me just go here and get started right here. So hopefully you've already done this, but go to that link that we provided, devcloud.intel.com, oneAPI, get started. Go ahead and sign in. Just click up here and sign in. Then scroll down, and once you're signed in, you're going to see this Jupyter icon down in the lower left. Right now, it's prompting me to sign in, but if I had signed in, it would just say launch Jupyter Lab. Okay. When I click that, I'm going to come over here to something that looks like this, and I'm going to just show you the launcher. It's going to look a lot like this. You're not going to see all these custom kernels that are built, but you will see these kernels, these Jupyter kernels for that use the oneAPI under the hood. One for PyTorch, one for TensorFlow, and one for just the broader oneAPI stuff. And if you scroll down further, you're going to see this terminal button. We're going to be using that terminal session down here. I just want to point out some things in the dev cloud. This is a navigation bar. I tend to like leaving this. This is this little folder in the upper left. If you click that, it toggles back and forth between full screen mode for presentation or showing you your file and folder structure. And I like that mode. The other thing is if you're like when you first start, you like having this launcher. It's like a safety blanket. And so what happens if you shut down your launcher? You can get your launcher back. See this big blue box with the plus sign on it? If you click that, you get your launcher back. So you can see, and then you can come down here and click the terminal. And we got a terminal session that would look similar to something like this. So let me just do a clear. And I'm going to just CD up to here. So I'm going to walk you through what we're going to be looking at is the GitHub README instructions. And I think Praveen has posted the GitHub location. And these instructions are what you would use to get the lab set up and ready to go. Really, for you guys' purposes, I am fairly sure that we can just get by with just doing these last 3 lines right here. So you won't have to do all of these. This is for other portions of the lab that we need for these. But these 3 instructions right here, just starting with the git clone. So this getting this GitHub repository itself, the git clone, and then CDing into the appropriate folder is what's key. So let me show you that. So I'm going to CD just from my terminal, just to kind of show you what we're talking about. Here's a list of all my functions. Or my folders. I'm going to CD into ML oneAPI because I followed those instructions. I did the git clone business. And here we go. If I do an ls here, I have a folder called machine learning. So I'll just CD into that. And you should see something like this. You should see 8 chapters or 9 chapters actually. Let me click a few times so you can see it. We have 9 chapters. We're only dealing with chapter 8 today. So if you CD into chapter 8, these are the notebooks that we're going to be playing with. Now let me show you from the navigation bar how we get there. So hopefully if you followed the instructions, you created a folder called ML oneAPI, and then you did a git clone, and that git clone created a folder here called machine learning using oneAPI. When you open that, you have 9 chapters effectively. We're going to go to the 8th chapter, chapter 8, Introduction to NumPy, powered by oneAPI. And here are all the notebooks. Now, I'm going to let you guys play a little bit. Most of these are fairly straightforward. I did put at least 1 to maybe up to maybe 3 roadblocks in every one of these notebooks. So you won't just be able to press run all and get to the end of the notebook, because it's going to error out, and you'll see the errors because there'll be nice bright pink boxes. Okay. And so you have to solve it. Good news is I put a hint there of explicitly how to solve it. But my goal here is to get you to think about, based on what I told you in the lecture, how would you solve it? How are you going to replace this loop with a single NumPy thing? And you may have to go off to Google, and you may have to do a search, or Stack Overflow, or the NumPy documentation itself, or whatever. But this is what you might do in the real world if you're going to reconfigure your software to really take advantage of NumPy. You're not just using a NumPy array. Everybody does that. how are you using the aggregations and the things, the ufuncs under the hood that really give you the power of NumPy, okay? And so there's going to be some roadblocks. So when you hit those, just go ahead and take some time to play with it. I think they're all fairly straightforward. You can get through these, it may take you past the end of this workshop to do it, but your dev cloud instance isn't going away anytime soon. You can play with this at your leisure, several weeks if you want. I would recommend that you do it somewhat close to our time now, so it stays in your memory. But just go ahead and play. The ones that I want to add more color commentary to are just this pandas one, because you may not get my point by just looking at the notebook. I'm going to take you through some scenarios. And so let me just walk you through that, and maybe the SciPy one as well. And then other than that, you're kind of going to be on your own devices to play with these labs. But I just want to start getting you familiar. So I'm going to start with something I'm going to call big, a variable, 100,000 elements. We're going to create a pandas data frame from it. It's got columns A through E. Then I'm going to create a function called myfunc, and myfunc is actually just computing the log effectively of that element. And so the first thing I'm going to do is I want to apply using I want to take that data frame and I want to apply that function to it over and over. Like every row, I want some log of that stuff. So the most naive sort of simple approach would be that you would say, well, you read on the internet somewhere that pandas iloc is really a way of accessing an explicit row column element of a pandas data frame. And so I want to take advantage of that. Now in this case, I'm saying iloc at whatever row governed by that loop at column number 2, go ahead and apply that myfunc to that. And so this is leading to something, and you're already thinking, I'm sure, oh, there's a much better way. There's a much better way. There's a much better way. We're going to get there. Okay. But I just want to show you some timings. So we do this, we get 7.5 seconds, something like that. And then you do some more web search, and somebody says, oh, never do that. Never do range when you're trying to access a data frame. That's silly. Use iter rows. Okay, great. So you follow that advice. Do the same thing, and sure enough, 6 seconds. We shaved off about 1.5 seconds. Cool, great. But then, you just keep asking, getting more information from Stack Overflow or whatever, and somebody's going to tell you to use, don't use iloc. You can use range, but just use at, or maybe you want to use, even the iter rows, but use at, right, instead of iloc or whatever. Okay, great. It's going to be a little bit faster, 6.5 seconds. Okay, great. And then the obvious solution, apply. Why didn't I use the apply function? That's what it's there for, right? So now you use the apply function. Apply for every row, the lambda x, for every row, you're going to apply this to every row. Okay, great. And we're going to take data frame at column A, do the apply, and we're going to assign that result to the column C. Great, we do that. And holy cow, 44x speed up. Apply is my new best friend. I'm never going to forget you. I love you, apply, right? Like, wow, I go get a beer, right? That was a great time. Should have known it, but you learn as you go. Okay, and then we're going to just plot these things. So here's the plot of our experience, right? And here's our pandas apply down here, very low execution time. Wow, that's cool. So, but now, next day, you begin, the data set's getting a little larger, and there's more weirdities. Now we've got this conditional logic we have to do. Well, that shouldn't be of a big deal. We'll just we'll just apply that. This is in a function called func. We'll just use our old friend apply, and we will apply that function. And it takes these columns in, A through E, and we'll assign that to a new column. Great, let's do that. It takes 81 seconds. And I don't know if that's good or bad, but I don't like to sit around for 81 seconds. Can we try some other tricks? Well, let's try using vectorization. Now, the first step in vectorization, we could think, well, let's just use masks. Let's just find the indices, the true false indices of all the data frames. So we're going to do the same logic, but just say, look, if the data frame at column E is less than 10 and the data frame at column E is greater than 5, we'll create a mask. And then what we can do is now we can use our old friend lock or iLock at that true false index, and we can create a new column called new, and we can assign these values from the data frame to it for that mask. And we can continue to do this for, we have different masks. We have, a mask for this condition. We have, different masks, and we apply it and we get the same result. And this is a 300x speedup. I mean, that's really 313x. Are you kidding me? But it's not very maintainable. It doesn't look very pretty. I may have made a mistake in here. So that performance comes at a tax, right? And here's just a plot of the performance. Okay, well, what else can we do? Well, now we're gonna make the problem even a little bit harder, because now not only do we have the conditional logic, but we're also going to apply a somewhat slowish function, slightly slowish function, to some of those elements conditionally, right? And so now we're complicating it. And so we go ahead and try our lambda function. And now in this particular case, different data size and so forth. In this case, it's 1 million elements. And with this particular case, we're getting executing in about 13 seconds. So this is a different scenario. It's maybe the third day, you've got another problem you're solving. And so this takes about 13.5 seconds. And then we say, okay, well, let's do that mask trick. That gave me a good benefit before. And sure enough, well, here we get a 5x speed up. Okay, well, that's, I guess, pretty good. That's good. Not as good as yesterday's result, but, pretty good. And then what we're going to do is we're going to try to use this fancy select statement that I was telling you about. This is one of the roadblocks you're going to hit here, because I gave you a hint. The hint is pretty doggone literal, but you can just replace the code between those bars with the hint and run this. And now we're talking about 2 seconds, 2.5 seconds. Okay. But that was just doing the, leaving the data frames as they were, whether they're integers or whatever they are. But I do know ahead of time that these were numeric values. So what if, instead of just taking the pandas data frame as it was, now what happens if we convert that to a NumPy array, right? So now instead of operating on the data frame directly like we were, and we were getting speedups from select statements, NumPy select on a data frame, we were getting good speedups. But now we're going to say, well, let's just get rid of the middleman, put it right in a NumPy array from the very beginning. And now let's try masking. Well, masking gives us 157x. Okay, great. Now we're going to use a select statement. We're still doing the NumPy conversion. We're converting the data frame to a NumPy array. And now we're doing the condition and the choice of the select statement. Well, this is 250x, 249x times faster, more readable. It's going to be more maintainable. I mean, it's as maintainable as your logic allows, right? And so now we plot those results. And so I just wanted to call this to your attention, because you may not get the idea if you're just reading it through, that this scenario is building kind of like over sort of like 3 days worth of experiments. And but this select statement business can really help even with a raw pandas data frame with the applies. It can also help if you convert, especially help if you convert that data to a NumPy array directly and now use a select statement. But it's pretty amazing. You can run it. You can use a NumPy select statement with the pandas data frame in its sort of natural form, right? So anyway, that's sort of the idea. And then SciPy, the idea, SciPy is like scikit-learn in that it uses higher levels of abstraction. So if the algorithm is not in scikit-learn, there's a good chance you're going to find an algorithm in SciPy. Okay, SciPy spans, if you're doing spectrograms, it's in there. If you're doing eigenfaces, or you're doing kind of any kind of eigen value, eigenvector sort of manipulations, it's in there. If you want to do numeric solvers, they're in there. Like in this case, let's say you're creating an atlas, from of Illinois, and so you're going to go from an atlas around, from Chicago to, to the facilities there at Argonne, or maybe down in Springfield, or wherever you're making this atlas. And so, you want to find the all pairs shortest path. Well, you might try Dijkstra's. You could look that up. Say, is that solve my problem? You just do a Google search, or in doing shortest pairs path search on Google, you'll probably find two names come up. One is going to be Dijkstra, the other is going to be Floyd-Warshall. And so this is a roll your own. This is how you would create an atlas if you rolled your own code. At least as simple. This looks like a matrix multiply too, by the way. Notice Floyd's algorithm. It's a triply nested loop. Instead of an operator where you take A times B plus C and assign that back to C or whatever, you're doing this minimum operation. But otherwise, it's very much like a matrix multiply. So that's the magic. Like, okay, this is so much like something else. There's probably a name for this algorithm. And so you have to go searching and figure out, oh, that's just Floyd-Warshall. But this is how you would do an atlas thing, rolling your own code. There's infinites, there's rivers and the lakes that you can't traverse. And so you have to go around Lake Michigan or whatever to get from one place to another. So those would be infinites. And so this is how you would code Floyd-Warshall by hand, right? And in this particular instance, with the size of the data I was looking at, 31.5 seconds. But you go do the Google search, you look up, Floyd-Warshall. Oh, that sounds like a good one. Hey, is that in SciPy? You kind of look at it. Yes, SciPy's got a version. And so this is what you do. You're going to take my little hint here. You're going to put this code in. Parenthetical comment. You can tell whether you're using the math kernel library, the oneMKL, in either SciPy or NumPy by using the show config function. So you can see whether the goodness is built in, and if not, you could do an install or whatever.
Hey,
But
Bob, sorry
yes,
to interrupt. So in this clone repository, what is the chapter number used?
Chapter 8. Chapter 8.
Or is there only one? How many chapters are there? How many modules?
Well, there's 9 total chapters, but we're only covering chapter 8 for NumPy.
Okay, thanks. Yeah, there's a question on that, so I just want to clarify that. Thank you. Sorry for the interruption. Go ahead.
And so you take that code, and I've already done it. I've already put the solution in here, but you use the SciPy. Well, this is I think the bad version of this is the improved version of the Floyd-Warshall. And so you can call it and look at the difference between using a SciPy version of it versus the roll your own. And in this case, it was 221x speed up. And this is just going to be the theme of the day for the most part. Now, I do have a lab down here about number 8. We're not going to I'm not asking you to do that. I'm asking you to do labs 1 through 7 and then number 10. Number 10 is on sorting. 1 through 7 kind of equip you with the syntax and equip you with the conceptual knowledge you need to kind of be successful with almost any kind of application that you're going to do. And then we're getting into the nitty gritty by looking at the matrix multiplication, because there's lots of ways you can do it. There's just tons of ways. You can use broadcasting, you can use SciPy, you can use a linear algebra package, you can use blah, 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 blah. So we compare them all. And you'll see that SciPy isn't always your best friend, but it's a good place to start. And then we're going to look at different ways of doing the NumPy pairwise distance. If you were with us before, we did with the Intel Extend for scikit-learn, I showed you a very rapid way of doing NumPy pairwise distance using scikit-learn. But that was using a particular metric. The metric was the cosine distance or the correlation distance. We did not accelerate Euclidean nor Manhattan distances. So this lab takes that further and shows, and I think Praveen showed you how to do it with Numba as well. But this takes this lab further and showing you how you can do that with the Manhattan distance or the Euclidean distance and different approaches using this vectorization kind of trick. But so these are what they are. I don't recommend those, are sort of like optional, like don't worry about those. But I would really concentrate 1 through 7 and then 10. And 10 is going to show you the advantages of you're going to do a heap sort, a merge sort, quick sort, whatever. Don't do the roll your own, use the NumPy version. And this is all with the intent. You're going to put your hand on the stove and burn your fingers doing roll your own. And it's intentional. I want you to learn not to do that. Okay. Don't burn your fingers. Take your hands off the stove and use the vectorized instructions. Go search for them. Don't give up. Spend 5 minutes doing some search, really, like maybe 10. Like the payoff is going to be aggregated over time. You're gonna get these payoffs. It's gonna be worth it. So go look, okay? And some of that, that's what we're doing. So the rest of this time is for you to play. Just start at lab number 1, hit a roadblock. And by the way, just to explain this graphic here, this graphic, if you're using Python loops with your NumPy arrays, you're standing in chest deep water and trying to walk. So just picture that. Okay, we've all been in a swimming pool, chest deep. How fast can you run? Okay, in chest deep water, not very fast. Waves are hitting you, it's even slower. Okay, so my goal here is to get you out of that chest deep water. Don't use Python loops if at all possible. Get rid of the Python loops, even list comprehensions, even map functions. Get rid of that stuff and use a NumPy equivalent instead. Okay, and now you've dried off, you've got your sneakers on and your running shorts, and you're on the beach and you're making amazing fast progress. Okay, so let this icon remind you of what you're doing when you're accessing a NumPy array from your Python loop. So anyway, go ahead and take through some of those. You're not going to get all the way, but kind of get up through this broadcasting. At least do 1 through 4. At least do 1 through 4. Okay, and if you can squeeze in 10, that would be great. And in other labs later, we're going to hit these other things more heavily. Okay, so just do what you can play with. These other labs that we're going to be talking about in June and in July are going to be kind of going into the hands-on of each of these other components, because there's quite a few here, I think you'll see. So just for sake of the shortness of the time that we have together here, just go through like 1 through 4, let's say, for today, something like that. And that'll be fine. So any questions?
I don't see any questions in the chat.
Okay.
Bob?
Okay. I'll just scroll through here and see if there's any color commentary. One of the things that we're doing here is I'm showing you the difference between rolling your own, using a map function, using a list comprehension, which this is all advice that you're going to get as a data scientist or whatever. Oh, just do that. It's going to be a lot faster. And it is, but it's not nearly as fast as using the NumPy equivalent. And this is the proof, right? You're going to see all this advice about, well, don't use the Python loop this way, use a map function, use a list comprehension. And yes, it is faster. But a lot of times I'll forget to tell you that you can do the same thing with NumPy. Because the presupposition here is you're already using a NumPy array with some of these things anyway. And so just use the list comprehension or whatever. But if you use the NumPy ufuncs, aggregations, fancy indexing, whatever. One of the fancy indexing examples that we have here, you're going to get about a 5 order of magnitude increase in speed. Be looking for it. And you use this all the time when you're going to deal with data science if you're dealing with time series data. Because time series data, you shift. Typically, you're going to take some data and you're going to say, I want to predict something in the future. So you're going to take your answer from the current and shift it down, 10 days or whatever it is. And so you shift it. And so when you do that shift, and if you're doing it on a lot of stuff, because typically it's not just one column that you're doing that way, but this fancy indexing lab is going to show you, and seriously, we get I think it's over 5 orders of magnitude improvement by using, instead of rolling your silly loop and doing it that way, you do fancy slicing, and it's incredibly fast. So
hey Bob, so can you just git clone the repo and navigate to the folder you're looking at? There are questions on there.
Yes.
There's a question. I have access to the link, but still struggle on a way forward to get started with NumPy.
Okay.
So if you can just.
Yeah, it's this link right here. It's just this GitHub link, and I'm going to show you. I'll just go back, and let's just create let's just go back to the beginning here, and we'll just create a brand new folder. Let's do it from the command line. Okay, shall we? I'll do a CD to get to my root folder, pwd. I'm in root. Let's make dir Bob temp. You're gonna call it ML using oneAPI, but I'm going to call it Bob temp. CD into Bob temp, like so. And then I'm just going to say, let's go up here and copy this git clone right here. Code, we're just going to copy it right here. I'm looking at the local HTTPS folder, tab, not the SSH one, it's HTTPS. I'm going to copy it. So it's in my clipboard. And now I'm going to just say git clone space, or, tab complete, whatever, control V. And this is that same link, and I'm just going to press it. And it will take 2 or 3 minutes to get the data, get the codes down here. So be patient with it, because as it is right now, you're getting a lot of extra stuff, all those other chapters as well, even though you're just focusing on chapter 8. I did create a repository with only the NumPy in it, but I haven't made sure that it's all totally clean. So I hesitate to give you that one. I've been doing more work on the big guy. So we're almost done here, and then I'll show you what to do to CD into it or whatever. So you'll realize that I just made a folder called Bob Temp. So here I am over here, right? If I go to Bob Temp, it's now currently building that machine learning using oneAPI folder. And now it's just almost complete. It's updating the files. There we go. And so now I'm good. And so now if I come over here, I go to chapter 8 down here, Introduction to NumPy. Just double click that. And now you get your 10 notebooks. And I just concentrate on number 1 for now. Maybe go 1 through 4. How's that? Just get through 1 through 4. And there are speed bumps. If you do this as is, and I'll just show you how this runs. I'm going to run all cells. I did this intentionally to make it so that you kind of get burned a little bit by doing run all cells. Okay, it won't complete. So, somewhere down here, run all cells. I keep looking for some pink. It's not done yet. It's thinking about it. Okay, somewhere about here. Oh, did I? Oh, okay. Yeah. Okay. Well, what I did is I had already modified this. I have a variable called like not defined or something like that, so that when you hit this roadblock, it will tell you, it'll give you an error sort of like this. Right? It's going to say, hey, you've got a variable that you're not using. Well, you got to get rid of that variable. And here's the hint. Here's what you do instead. Right. So you're going to hit 2 or 3 of those roadblocks, and I put them in there intentionally. I know it's kind of ugly, but there's so much temptation to just do a run all and just kind of go, and you're not going to think about what you're doing. So even though I gave you the hint, like I want you to think through what we're trying to do. We're trying to emulate this behavior of this list comprehension. We're trying to take the log of I+1 for every element. How would you do that in NumPy, right? And I gave you the hint. Try to do it without the hint. But if you get totally stuck, just use the hint, right? And then, you could just do this. But at least it slows you down to make you stop and think about, how do you vectorize that? How do you solve that challenge? And when you first start, the first 1 or 2 or 3 of these, you're going to really think, well, that's so easy. Oh, that's so dumb. And then you try to do it and you're like, wait a minute. How do you do that? Wow, what do you do? And that's the level you got to get over. You got to get over to the point where it's like, oh, that's so easy. You just do NumPy, blah, 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 do this, blah, blah, and poof, you got the answer, right? So that's the goal. That's the level I want you to get to in chapters 1 through 4, let's say right now. And if you get time, do 10 for sorting, since I alluded to it today. But, did that help? Are you able to get the GitHub going?
Sorry, I was on mute. Yeah, I think that helped.
Great. Now I know, because I've been here. I can't tell you how many projects that I've done as a data scientist where I'm doing the proof of concept. And so I'm looking at the algorithm, and I create some dummy fake little data, 100 elements, and I stuff it in a list, and I do my business, and off I go. And I prove the algorithm works. And so then I do the silly thing of saying, oh, well, then all I have to do is get rid of my dummy data, and I'll plug in that real data that's a billion elements. And the thing is molasses slow. It takes hours and hours and hours, sometimes days to complete. You're like, what? And you control C is like, what's going on? And if you go ahead at that point and you look at the NumPy equivalent of whatever that is, doing that low level stuff. If you're doing high level stuff, you do SciPy or scikit-learn. If you're doing low level stuff, if your loops are low level stuff, you do this stuff. Okay, so you have an answer for each. And if you do those replacements, like I told you, that Airbus guy thanked me profusely on LinkedIn because he took that class and he's like, I got 60x speed up. He was doing it on his laptop now. He was analyzing that data. He was, if you could just imagine a guy writing effusive, notes in a LinkedIn chat to me personally, and he's almost like doing backflips. He was so excited. So do the investigation. It may pay off for you. Again, just a quick wrap up here. Thank you for your attention, guys. I appreciate it. We've concluded the live demo part. You can keep playing in the lab. There's no, we're not going to shut the lights out on you. You can play as long as you want to, for days, weeks, if you want. But I did want to just leave you with that poll, just a hand waving poll on the chat. Just fill in the chat. Are you right now, or do you plan to use any of these tricks that I've showed you in your code, either for NumPy, pandas, SciPy, scikit-learn, those optimizations that we didn't cover today, but we've covered in other labs, Numba, PyTorch, TensorFlow, the Intel extension for PyTorch, the Intel extension for PyTorch and TensorFlow, the Intel neural compressor to do a model optimization, Modin, XGBoost. XGBoost is really popular in Kaggle competitions for doing both regression and classification. It was one of the things that won probably 50% of the Kaggle competitions. So many of you may be using XGBoost. Well, we built those accelerations in there, and we also accelerate even more so if we use the oneDAL library, which is also part of this Intel extension, this AI analytics toolkit. So if you're planning on using any of those things in your code, or you're doing it right now, if you could just put in the chat, yeah, we're using it, or we plan to use it, because that means you're using these optimizations on your hardware. And so while you're doing that, let me just move on to the call to action. So the idea is you're going to find large loops, doubly or triply nested loops, even large list comprehensions, whatever, and you're going to replace those with an alternative, either NumPy itself, if it's low-level things that you're doing, or scikit-learn, if it's higher-level stuff, or SciPy, if it's higher-level stuff. You can use it to replace pandas, not replace it, but to accelerate pandas. Okay. You can find the time-consuming list comprehensions. You replace those with a NumPy alternative. If statements, just because you have if statements in your conditional logic, in your loops, don't lose hope. You can use the NumPy where select clauses and still get it to vectorize. So these are the call to actions. Look for these opportunities.